So, we have done all the statistics and so on up to now about likelihood ratios, probabilities and things like that. Now, we will apply, let us apply this to the waveform of the signal of compact binaries. Okay. So, we have compact binaries which are there, and as we saw, there have been so many discoveries or so many events which have been discovered on the LIGO detectors, and now lately finally there was the Virgo detector which came in for the last two events. So, these kind of objects, how these things were detected. So, what I am going to describe here is the absolutely the first attempt as doing this analysis. This was back in 1991, and I will describe that how that was done. That is the simplest, we take the simplest model for the compact coalescing binaries. So, you have two stars which are going around each other, they are compact. We need them compact because we need to get to the bandwidth of the detectors, which is of tens of hertz to kilohertz. So, unless they are compact, they will not rotate around each other fast enough, so that they produce signals in the range of tens of hertz. So, they have necessarily got to be compact binaries, and those are neutron stars or black holes. So, we take two black holes or neutron stars or neutron star and a black hole thing binary. They go around each other, they emit gravitational waves. As they emit gravitational waves, they lose energy and they fall towards each other. And as they do so, they finally coalesce, and you get a waveform going from the point you observe them, say they come into the bandwidth of the detector, and then finally they coalesce. So, here is the waveform for the inspiraling compact binary. So, we are taking a very simple waveform. So, first we will not first, but in fact, most of this lecture I will be talking only about that. So, neutron stars or black holes spiraling in together, waveform can be cleanly modeled, and we take the waveform which is the most simple. It is just one term, and it comes basically from, it is called the Newtonian waveform, and it comes basically from the quadrupole formula. You have seen the quadrupole formula in earlier lectures. You apply this quadrupole formula to a binary star system. So, you have compact two stars like black holes or neutron stars going around each other. As they go around each other, they emit gravitational waves. You calculate the gravitational waves using the quadrupole formula, integrate over the whole sky or at a sphere at infinity, and you get the energy loss. From this energy loss, you put that into the Keplerian orbit. So, you have the Kepler's law telling you how the orbit should be, but if the energy is lost, this orbit will start collapsing or becoming smaller, the period will increase. So, finally, you get a waveform which looks like this. First of all, the frequency starts increasing because the stars are coming closer together, period is decreasing. Also, the amplitude increases because the quadrupole increases, the third time derivative, the second time derivative of the quadrupole increases, and you get this particular waveform. So, this is the simplest waveform, and we are not going into the more complicated waveform where we have post-Newtonian terms, but we will go into it at the later part of the lecture, and we will see what happens there. So, then the H looks like this, as I have already written down here. It is the M, which is called the chirp mass. It is a certain combination of masses of the binaries. It is roughly, if you take one solar mass binaries, this chirp mass turns out to be 0.88 if they are equal mass binaries. But if this chirp mass is of the order of the sun, then the H is of the order of 10 to the minus 23 if these binaries are like 100 megaparsecs away, and the frequency is at something like 100 hertz. And so, H is minus 10 to the minus 23, your noises are also at this level. So, clearly you need to pull out the signal from the noise. So, this is the signal. So, we use the match filter, but the waveform is embedded in detector noise which has comparable or larger amplitude. So, use the match filter. So, that is the answer. So, the match filter is basically you correlate the filter, the match filter which we saw earlier how it was derived. This is just the template, it is called. That is, you take something like the signal and you divide that by the PSD of the noise, that gives you the match filter. You correlate it with the data, integrate, and this is the formula which is given here, which tells you what is the formula for C of tau. and it is best to do it in the Fourier domain, because then you can use the FFT. So, we can get the correlation at all times, so at one stroke. So, it is like instead of doing whole lot of calculations of this x of t times q of t plus tau, where tau runs over the whole data segment, you would have to do n integrals, which you could amount to order of n square operations. But with the fast Fourier transform, you just need n log 2n operations, order of that, and which brings down your operations by a huge amount, like something like order of 10,000 or 100,000 for a particular, for a specific or a typical data train. And this is the optimal filter, as we see in Gaussian noise, and basically it is one of the best filters that one can use. So, match filtering the inspiring binary signal looks something like this. So, the top part of the figure shows the signal which is there. Of course, the signal is coming all the time, but here it shows where the signal starts. So, that signal is the signal starting point is the point where the signal enters into the bandwidth of the detector. So, that is the point where it starts. So, that is what is called the time of arrival. When the signal, so if you have two stars which are falling close to each other, as they are, when they are rotating itself, they are going around each other, they are emitting gravitational waves. So, when do you say that the signal has arrived? You say the signal has arrived when the signal comes into the bandwidth of the detector, because the signal is increasing in frequency. Finally, it will reach that minimum level of the bandwidth of the detector, say 10 hertz or something like that for the advanced detector, and it will come into this thing. So, that is the time of arrival. There is also a phase at arrival. The phase can come at any time, that depends on the history. So, that is the phase at arrival or phi naught. We will see that later on. So, you get this particular signal which is there. Now, if you reduce the amplitude of the signal and put it in the noise, you can't see anything in the middle figure. So, it is the whole data which is here it is labeled as S of t, but it should be x of t. And now, you take the correlation. If you take the correlation of this, the match filter, you get a peak suddenly at this point. It is the peak which is at the time of arrival. You can see that the peak coincides when the signal starts over there. So, this is the match filter. So, match filter not only tells you that you have detected a signal. Now, if you put a threshold under the peak somewhere there, it will tell you with what significance, what detection probability that you have, what is the false alarm, what is the detection probability that you have detected the signal. And it not only tells you that it is detected the signal, it gives you also the parameters of the signal, like the time of arrival, phase of arrival, and so on. So, simplest waveform, the simplest model is waveform with one mass parameter, and this was one of the papers of 1991 and 1994. The waveform depends on many parameters, in particular on the two masses. In the Newtonian approximation, it depends only on the combination of the masses. This is the simplest possible waveform. The chirp time, which is called tau naught m1 m2, that is a more convenient thing to take than the mass. So, it is basically the reduced mass multiplied by the total mass to the 2/3, and that raised to 3/5 is what is called the chirp mass, and tau naught is it is related to that chirp mass in some fashion. So, then the signal now can be written as it is a function of t and parameters. There are 4 parameters: the amplitude, the time of arrival, the tau naught, that is the chirp time, which is in fact the masses of the binaries, and phi naught, which is the phase at arrival. And it looks something like this, which is a times slowly evolving amplitude, which I have not written down there, it is not important for our purpose, and a phase phi of t minus Ta tau naught plus phi naught. And the parameters, as I pointed out, are 4 of them: A, Ta, phi naught, and tau naught. Amplitude, time of arrival, initial phase, and chirp time tau naught. Now, extracting the amplitude. How do you extract the amplitude from this? You have the data x. So, if you have stationary Gaussian noise or wide sense stationary Gaussian noise, then the template S is taken to be normalized. So, what you do is you normalize the template by using the scalar product S comma S equal to 1. So, Sx now here is, this is not the ensemble average, by the way. In this particular slide, These angular brackets in fact show the scalar product. It is 4 times which we had written down S star of f, x of f, sh of f, df, where sh is the one-sided power spectral density of the noise. And we use normalized template. You normalize the S so that it has unit amplitude. Then h is a times s, and a is called the amplitude. Now, when you take the correlation, which is in fact, as you saw, it was basically the likelihood ratio in disguise. It is just that C is in fact, lambda is a monotonic function of C. So, one can use C. C is S, the scalar product of S with x, but S with x is S comma h plus n, where the h is the signal plus the noise. Now, if you divide this thing into S comma as plus Sn, you get a plus s comma n. But the average value of Sn is basically 0, because you have got the mean noise 0, and you can see that. You can actually prove that this particular average value of the scalar product of the template with the noise, where the noise is 0 mean, is in fact 0. So, average of C, or the estimated value of C, turns out to be the amplitude. So, you get an estimate of the amplitude by simply looking at the correlation or taking the scalar product of the data with the template which is normalized. So, that is how you extract the amplitude of the signal. So, the parameters are A, Ta, phi naught and tau naught. So, the strategy is, for amplitude you use normalized templates. For the initial phase, you do not have to search all over phi naught. That is also one of the things which we had pointed out. There are only 2 templates which are required, phi naught equal to 0 and phi naught equal to pi by 2, and one can in fact make a linear combination of these 2 templates and get any other template for any other phi naught. And then you can add them in quadrature to get to maximize, because finally we want to maximize over the likelihood ratio, and maximizing the likelihood ratio is maximizing the correlation or the scalar product. Then scanning over the time of arrival is done in a very efficient way by using the fast Fourier transform, as I have already shown. But for tau naught, this is the dynamical parameter or the mass here. For that you need a discrete bank of templates. You cannot do this with any other way. We do not know any quick way of searching over this. So, what we do is we densely pack the parameter space with templates. So, suppose you are searching in a mass range from 1 solar mass to 30 solar masses, the tau naught will range in a certain range. So, in this range you have to make templates in a certain way. So, I will show you how this is done. So, anyway, let us see how this phase is in fact extracted. The phase is extracted by in this way. So, I explicitly show how this is done. The waveform is given by h of t and so on equal to a into this and so on. But now cos of phi minus phi naught is cos phi naught plus sin phi naught. This is the identity. This is the identity we use. And now if we use templates for phi naught equal to 0 and phi naught equal to pi by 2, and just calculate 2 correlations. The template at phi naught equal to 0 and phi naught equal to pi by 2, just you make 2 templates which are normalized and take the correlation with the data, and those are denoted by C naught and C pi by 2 as over here. Then C at phi naught is simply given by C naught cos phi naught plus C pi by 2 sin phi naught, just because of this identity up there. So, you do not need to do this calculation for more than 2 templates. You can search all over phi naught by this particular with the simple relation, and that is because of the symmetry in the waveform. So, all these things, the fast Fourier transform, the searching over phase, comes because of the symmetry that exists in the particular waveform, or which is basically a group theoretic symmetry. So, only 2 scalar products need to be computed for phi naught, and moreover maximum of C phi naught is just adding the 2 C naught and C pi by 2 in quadrature, and if you like you can take the square root of this thing to make the statistic. So, what is the detection algorithm for a single mass parameter? You take the data x of t, then you use normalized templates s of t semicolon t naught, s pi by 2 semicolon tau naught, and fix tau naught. So, fix a tau naught, use for a fixed tau naught, use FFT to compute C naught of tau, C pi by 2 of tau, where tau is the time lag, and this will scan over the TA. So, with one stroke you have got C of C naught of tau, C pi by 2 of tau using the fast Fourier transform. Then the statistics can be maximized over phi naught by taking the quadrature C naught square plus C pi by 2 square for tau, for each tau. So, it is an easy algebraic operation. So, conventionally we could always use C squared of tau for doing our detection, but conventionally we still use its square root C of tau. But for tau naught, as I said, we require templates. So, we need to search in tau naught with a dense family of templates. So, that is what we do. So, what we do is we take the whole tau naught axis and we have to take templates for different tau naughts and densely packed, and then take the maximum of C of tau over tau naught and all that. We have already taken maximum over phi naught, and amplitude does anyway come out, and then compare it with the threshold, which will be set by the false alarm probability. I have already covered this false alarm probability earlier, but I will talk more about it later in the from the point of view of astrophysics. So, searching over tau naught. So, the searching over tau naught is done like this. So, we define what is called the ambiguity function. So, this is the function which is basically the scalar product, it is cos theta basically. So, S of tau is unity, the norm of S of tau is unity, norm or the modulus of S of tau naught plus delta tau naught is unity, because we are taking templates which are normalized. If you take the scalar product of two unit vectors, what you get is the cos theta basically. So, this is the cos theta, H delta tau naught is what comes out here, it is where, so that is why we have taken tau naught here. Tau naught is like a Cartesian parameter for this. So, H delta tau naught is written like this, and it is plotted here. Here it has been plotted for LIGO 1, this was the initial LIGO power spectral density, and so on, and Fi is 40 hertz and Fu is, Fl is 40 hertz, and the lower frequency is 40 hertz, while the upper frequency cutoff is 512 hertz. So, this is the function H, which is plotted against delta tau naught. Delta tau naught is 0, that is where it is the maximum, and that comes straight away from the Schwarz inequality, because the scalar product is maximum when the two vectors are pointing in the same direction. So, this is 1, and then it falls off. So, then how do you choose your bank of templates? So, you need a discrete bank of template in tau naught. You choose it by taking something called the minimal match. So, you allow for a 3% loss. So, this is very subjective. Suppose we allow for something like a 10% loss in the number of events we want to detect, okay? We can't help it. So, about 10% loss we can tolerate in the number of events we can lose. Then that means it is 10% in volume. Now, if you take the cube root of this volume, the 10% loss, it turns out to be 3%, because the volume scales as r cubed. So, the minimal match is set at 1 minus this maximum mismatch that you can have, that 3%, it is 97%. So, you let the H fall something like 97% and measure delta tau naught from this. So, you space the templates like at the rate of at the distance of 2 delta tau naught. So, one template covers a region of something like 2 delta tau naught. The next template will pick up where the first template has left off, and in this way you can scan over all tau naught having a discrete bank of templates. It is a continuum. So, continuum you simply cannot scan with the finite computational resources that you have, and tau naught is given here in terms of the chirp mass, which I have written here, which is it's like something like 35 seconds for where the chirp mass is something like that of the sun, and the lower frequency cutoff is at 40 hertz, which is the where the bandwidth of the detector starts from the lower end. And the chirp mass is, as I said, it is mu times m to the 2/3. Mu is the reduced mass, m is the total mass. Okay. So, this is how it is done. So, you have got a whole lot of templates which are there. And then you maximize over things. Now, let us see this little bit more in more detail. Now, we take a more complicated waveform. The real waveform, the Newtonian waveform is really not good enough because of the fact that the phase does not match very much properly. You need, for match filtering to work properly, you need to know the phase extremely accurately, and you need a whole lot of post-Newtonian terms you have to add into the waveform in order to detect the binary. Why you need post-Newtonian terms? Because in general relativity, nobody so far has given a exact analytical solution for the two-body problem. You know that a two-body problem can be easily solved in Newtonian mechanics. It's already there in textbooks like Goldstein and so on. But here you have to make approximations, use numerical relativity and so on to actually get the waveform. So, let us look at this post-Newtonian corrections. So, if you make some post-Newtonian corrections, then the two masses become non-degenerate, and the waveform now depends on both the masses, and you take two parameters which are tau naught and tau 3, which are more convenient functions to handle for the data analysis, and they are given here in terms of the masses and so on, and the Fa, which is the fiducial frequency that one has taken. So, if you take a mass range from 1 solar mass to 30 solar mass for the individual masses m1 and m2, the space looks something like this. The parameter space looks like this. This is the space over which you have to search. You have to search over the 1 to 30 solar masses. So, tau naught ranges from 0 to 1.4 roughly seconds, while tau naught ranges up to 42 seconds or 43 seconds or something like that. And it is a triangular shape because this is a shape waveform which is symmetric in M1 and M2. You can interchange M1 and M2, you get the same waveform. So, you have to search only in a triangle in the space of masses. So, that triangle gets deformed into a thing which looks at least topologically like a triangle. Now, this has to be searched now. So, this is a two-dimensional, slightly more complicated problem. The thing which has been done now for the discovery, the waveform is even more complicated. So, in this case now we have the ambiguity function. Now, this depends on, it's more general. So, in general the ambiguity function is written as, it is a function of lambda alpha, the point on the parameter space lambda alpha, and the distance delta lambda alpha. So, it is the scalar product of S lambda alpha dotted with S lambda alpha plus delta lambda alpha. So, the intrinsic ambiguity function, basically that is the normalized one, is basically this, which is maximized over delta T c and delta phi naught. We can do all these things because we can easily over T c or T a over the time of arrival and over we saw, we can do this search quickly by using fast Fourier transforms and over the phase by using just two templates. So, the reach of a template. So, if you take a template at the origin where delta lambda 1 and delta lambda 2 are 0, and you put take the mismatch or the minimal match or maximum mismatch to be epsilon or the minimal match to be 1 minus epsilon, then the template can reach in a sort of a ellipsoidal or elliptical region. In a higher dimensional space, it will be ellipsoid, hyperellipsoid or something like that, and you can in fact write it in terms of a metric or a quadratic form which looks like this: g alpha beta delta lambda alpha delta lambda beta equal to epsilon. This is a quadratic form, and that gives you in fact a ellipsoid in 3 dimensions, ellipse in 2 dimensions, or hyperellipsoid in higher dimensions. So, this is the reach of the template, and this is plotted for epsilon, and epsilon we choose equal to 0.03 or 3%. So, the parameter space, you take a small piece, how do these templates look like? How do we arrange these templates? Here is a picture which shows this. So, this is the picture, this is called the hexagonal tiling of the parameter space. So, that block which was here, this rectangle here has been blown up, and the templates are placed at the centers of this ellipses here. So, there is tau naught and tau 3, and you cover the parameter space by this ellipses over here. The minimal match has been chosen to be 0.97, and the density of templates is like something like 1300 per second square, and the area of this thing is something like 8.5 second square for LIGO 1 PSD or initial LIGO PSD. I have done it for this thing because this is a nice example or a simple enough example to explain. So, what this tells you are there are about like something like 10,000 templates you get for the initial LIGO, and one has to in fact search over this whole lot of templates in order to search for the whole signal between 1 solar mass and 30 solar masses. And as I said, you can search over the TC or a TA, the time of arrival, and phi naught very quickly using FFT and quadratures. Now, thresholding. Now, you come to the statistics. So, if you are in Gaussian noise, the C naught and C pi by 2 is Gaussian distributed with mean 0. Then, if you take just the noise in absence of the signal, if you have no signal, then C is in fact Rayleigh distributed, and the Rayleigh distribution is given by this expression C into exponential of minus C squared over 2. And if you take a false alarm of 1 per year, so this is where you fix the false alarm probability. So, how do you fix the false alarm probability? You have some estimate of the number of events that you are going to observe. So, suppose you think that from astrophysics that you are going to observe like 30, 40, 50 or about 100 events, you might tolerate one false alarm in a year. So, this is what is done here. So, one false alarm is allowed a year. Then in that case, you sample at 2 kilohertz, and there are something like 10,000 templates, as I have said, at 3% mismatch. Then you have a false alarm probability of an extremely small number. The alpha is extremely small, and you must put a threshold on C, something like eta of 8.2 sigma. So, eta to infinity RCDC should be equal to PF. This is extremely small. One can calculate what this is going to be. One false alarm a year with 10 to the 4 templates. So, this means something like 2 kilohertz sampling. So, there are 10 to the 10 points, NT is 10 to the 4. So, PF is of the order of 10 to the minus 14 or something like that, and for that you get eta of 8.2 sigma. So, that is how it is done. So, all that analysis which I showed you is this. We are using the Neyman-Pearson criterion, and we are using maximum likelihood because there are so many, there is a whole family of signals. The signals are distributed in TA, the parameters are TA, amplitude, everything, amplitude, the time of arrival, the phase and the masses. And then you have to calculate the detection probability, and this is if the signal strength is C for a perfect match of the template, C follows then a Ricean distribution if your noise is Gaussian. With 2 adjacent templates and 95% detection probability, you must put your threshold like eta plus 0.7 sigma. So, S min is 8.2 plus 0.7 plus 3%, it gives you 9.2. So, if you put a threshold of 9.2 for your signal, you detect a signal with 95% confidence or 95% detection probability with a mismatch and so on. So, that is the basic game that we have been playing. That is, we have a false alarm, we have a detection probability, we have to search over the parameters with a whole lot of templates, and we can search over some parameters very quickly, efficiently, and that helps in saving computational resources. So, now I come to the discovery of gravitational waves, the merger of 2 black holes, the first discovery, the first event which was discovered. In this case, the waveform is far more complicated. Now, what we have done is we have just used in the first case I had used only the Newtonian waveform, then I added the post-Newtonian terms, but now we have to use the full waveform. So, the post-Newtonian expansion can go up to a certain point. After that, numerical relativity only can give something, and then perturbation theory when the black hole rings down and settles into a stationary state. So, those are the two detectors which observe the waveforms, and the waveforms are shown in both the detectors, and the waveforms have been moved by 6.9 milliseconds because the signal appeared in Livingston 6.9 milliseconds earlier than Hanford. So, there are these 2 detectors in Livingston and Hanford. So, it arrived there, but then they are shifted by that 6.9 milliseconds, the Livingston waveform, and they are placed one on top of each other. And only 10 cycles were seen, and from 30 hertz, and the waveform vanished in something like 0.2 seconds because the masses were so large. If the masses are large, the things fall together quickly, and within 0.2 seconds the whole signal disappeared. What are the data analysis? The data analysis here was 16 days of data from September 12 to 20th October. It was that time when the signal thing was announced. But here now the noise is non-stationary and non-Gaussian. So, what do you do about the statistics of the noise? So, the statistical properties of the noise now must be determined empirically. So, this is done by artificially shifting the data streams by offset large compared to the light travel time or the gravitational wave travel time between the detectors. So, suppose you slide the data by an amount. So, the light travel time between the detectors is something like 10 milliseconds, and you allow for some shift error because of the noise. So, you take something like 15 milliseconds as the thing, and if you take a time slide of more than 15 milliseconds, then you do not expect a signal to be there if you match these two data streams and add them in quadrature and so on. Also, a Bayesian approach was followed. So, our approach was in fact what is called frequentist. It is a maximum likelihood, but now Bayesian approaches are followed, where you put in a prior and all that from whatever knowledge you have of the distribution of sources. So, this event, the first event which was detected and which marked the discovery of gravitational waves and binary black holes and so on, which was a historic discovery. In fact, I would call the discovery of the century. Okay, so, this is something like that. It was this particular event GW150914, and the parameter space for that. Now, the parameter space was not 1 to 30 solar masses, but the masses were running from 1 solar mass to 99 solar masses, and also things were M1 plus M2 was less than 100 M sun and so on. And also one had taken an effective spin, which was aligned spin, and so there were several dynamical parameters, there were phases, there was time of arrival. So, the parameter space was much bigger, and the waveform models also were what are called effective one body, numerical relativity, combinations of this, and these are the inspiral, merger, ring down waveform. So, the first part is inspiral, which is given by the Post-Newtonian approximations, the merger is given by the numerical relativity, and the ring down is given by the perturbation theory. And this is the IMR phenom waveform, it is called, because you can do it only in very few places, because we do not have too many such simulations from numerical relativity, only a few hundred, while the number of templates required is 250,000. So, we have to in fact interpolate for waveforms in between. Then you compute the statistics rho of t from both the detectors. The output of both the detectors is added in quadrature within a 15 millisecond window. So, you take the time delay between the windows not more than 15 milliseconds, because that is the distance between the detectors is 10 milliseconds, but you allow for 5 milliseconds because the noise can throw off the trigger a little bit. So, 15 milliseconds is wide enough margin for this, and the signal to noise or the correlation turned out to be 24 for this. And what was the statistical significance? The false alarm was something like less than 2 into 10 to the minus 7. So, one part in almost, or 2 parts in 10 million, that this is noise, and rest of it is signal. So, this is the kind of huge detection, that probability that we have detected this particular signal. And if it was Gaussian noise, it corresponds to 5.1 sigma. That is just a way of saying it. So, concluding remarks. So, as I have shown here, data analysis is an essential component of the discovery process. You just do not, just having the detector is not enough. So, laser optics, lasers, vacuum technology, control systems, all these things are there. But in addition to that, you need high performance computing, you need data analysis, statistical methods, mathematical methods in order to extract the signal from the noise. And all this now, this whole effort, including data analysis and all that, has given rise to a birth of a new astronomy, and that is gravitational wave astronomy. So, this is the beginning, it is not the end. It is not as if the gravitational waves have been detected and that is the end of the story. A new field has started and a new astronomy has started. So, this is the beginning.